Now you should see the design of C amplifier, which is the second experiment in AEC lab. So this is a circuit of C amplifier. So we can see now there is a supply voltage plus VCC and the ground. R1, R2 are the resistors used for providing the bias. CC is the coupling capacitor and V in is the input voltage. RC is the load resistor which is connected in collector and the VCC, and the output is taken at the collector. So RE is the emitter degeneration resistor and CE is the bypass capacitor. The resistors used are quarter-watt resistors as per the design values of resistance we'll use, and RE is realized using a pot with two terminals connected to one to emitter, one to ground, and the third terminal is connected to the bypass capacitor, which is usually electrolytic capacitor. CC is the coupling capacitor, which is usually ceramic capacitor, and the transistor that is used will be usually SL100 or VF194. So we shall see how do we proceed. Now you can see this is the same circuit by removing this coupling capacitor and taking out the output. Now this is purely we have not connected the input. Now this is the DC conditions. The voltage across RC is no, of course will be written as VRC, and the voltage between base and emitter is VBE, and voltage across REV is named as VE, and the voltage at base point with respect to ground is named as Vx, and we assume a current of base current IB flowing through the base, and IC is the current that is flowing through the collector, and we'll assume a current of I1 flowing through R1 and R2. So this is what is the basics we'll be considering for designing the DC bias. Okay, these are the design equations used for this circuit. So IB is nothing but the base current, which is equal to the collector current divided by the beta, which is nothing but the current gain constant, and I1, this current which is flowing from VCC to ground through R1 R2 is named as I1, which we are assuming it to be 10 times IB. So since it is the current flowing through R1 and R2, neglecting this base current, we write the expression for I1 is equal to VCC by R1 plus R2. So using this equation, we can write R1 plus R2 is equal to VCC by I1. And we know the expression for collector current in terms of reverse saturation current, the base emitter voltage and the thermal voltage is given by this expression. So this equation can be rewritten as equal to VB is equal to VT into ln of IC by IS, where IS is the reverse saturation current, which will be very small in quantity. And we know what is this Vx voltage, which is at the base point with respect to ground, is equal to VBE plus the base VB, which is nothing but base emitter voltage, plus the drop across the resistor RE, which is named as VE. And we can estimate the resistance of R2 because we know what is Vx, which is nothing but VB plus VE, and we'll be knowing what is I1. So R2 is given by Vx by I1. So using this equation 1, we know what is R1 plus R2. Using this equation 2, we know what is R2 is. So VB is nothing but IC into VE. We can VE is usually assumed as 100 millivolt, a very small fraction of that supply voltage, so which is equal to IC into RE. Now this IC is almost equal to IE. We approximately write it as IC into RE, so that we can estimate the value of RE, which is nothing but VE by IC, because VE we are assuming is 100 millivolt, and IC will also be assumed as some current which is usually 1 milliampere. And from equation 1 we can write this 1 and 2, we can write R1 is equal to VCC minus Vx by I1. Now this is VCC, this voltage is Vx divided by I1, the current flowing through that will give you the R1 value. So we can get the value of R1 as well as R2, and of course the RE also. Next, okay, in the actually design, so we are supposed to know what is the value of R1, R2, RC, RE for a given specification of IC is equal to 1 milliampere and VB of maybe around zero point 0.6 volts, 0.6 volts. So with these parameters, with these equations, we know what is the value of R1, R2, RE. So RC can be estimated from the equation where RC is given by GM, where the voltage gain is given by GM RC divided by 1 plus GM into RE dash. So this RE dash is the resistance which is unbypassed by this bypass capacitor. So this is RE dash. So where GM is the transconductance of the transistor, which is given by IC by VT. So if you consider the value of RC to be 2.2 kilo ohms, which is for a maximum swing, if you are assuming a current of 1 milliampere, so you're going to have a drop of 2.2 volts. So this will be around 2.8 volts with the VCC as 5 volts. So we're going to have a optimum swing for this particular circuit. So we can estimate the value of RE dash for a gain of 50 or whatever the specified gain. So let us see a typical design. So a typical design, we have assumed, okay, let the AV to be, the magnitude of AV to be 50 with an assumption of collector current as 1 milliampere, VCC as 5 volt, beta as 100, IS, the reverse saturation current as 10 power minus 13 ampere, the thermal voltage VT is equal to 26 millivolt. So using the design equations 1 to 4, we obtain the expression values of all resistors as these values. Now these are not the standard values, so we go for a nearest possible standard values of all the resistors, which is listed here. So we have R1 as 47k, R2 as 6.8k, and RE is a 100 ohm part, and RC is equal to 2.2k. So let us see the flow chart of design, how we can proceed. So this is how we have done the design of the C amplifier. First we'll start with the given specifications. So AV is assumed to be 50 and IC is given as 1 milliampere, VCC is given as 5 volt. We'll make some assumptions. So VT usually 26 millivolt, IS for a given transistor it will be around 1 into 10 power minus 13 ampere. VE is assumed to be 100 millivolt and beta is 100. So then using the equations 1 to 4, we got the values of R1 to R2, RC as well as RE. If the values are not standard one, so you go to the nearest standard values. Then you again cross check with these modification in the values, is your designs are well within the tolerance. If you're satisfied with this, then you can go and conduct the experiment. If you're not satisfied with this, you can go back and change the standard values so that you get the desired value of AV and IC. So that this is a way how you can design your amplifier with the equations, and this is a flow chart. So first you are assuming the assuming the constants, and then you are designing the values of R1, R2, RE as well as RC. Then you use the standard resistance, then you again cross check. If you're okay, then you can proceed with the conduction. So this is how the conduction start. So first you start with the biasing circuit, which is exactly over here. If you are satisfied with VB and IC, so this is VB, you can measure VB, and what is the value of IC, that is you measure the voltage across the resistors, divide by the resistance, will give you IC. If you are satisfied with this, you can go to second circuit. Otherwise you may have to check the VCC connection, BJT, check it, and then adjust the R2 values. If you are through with that, you can go to the second circuit. In the second circuit you are having only the extension of this one. Here you are connecting a coupling capacitor over here, and then you apply the input voltage. So care should be taken that okay, you are applying a sine wave of 100 millivolt, very small in amplitude. Keep the frequency around 20 kilohertz. Then you check what is, if the AC signal is amplified, then you can proceed. If it is not amplified, check the value of RE dash, whether it is minimum or not. So what do you mean by RE dash minimum is, so as you can see in this previous circuit, so we are supposed to have this RE dash. So this should be minimum. So we have this RE dash. So this should be there over here, so that you are bypassing the entire resistance, so that you'll get the maximum gain over here. So meaning, suppose if you are thorough with gain, then you can see you're connecting the circuit in figure 2, applying the input voltage with a coupling capacitor. If it is amplified, you can proceed. If it is not amplified, you check the value of Re whether it is minimum or not. So then if you are thorough with that, then you can measure the input voltage, output voltage, do the frequency response, measure the voltage gain at various input frequencies, and you can measure the bandwidth. So this is how the input voltage looks like. It can be 100 millivolt or 10 millivolt. So you can see now this is the input voltage sine wave with a frequency of 20 kilohertz. Of course, this can be 10 millivolt or it can be 100 millivolt depending on what is the gain of the amplifier. So you connect this to 1 plus of the AD gate. So this is to 2 plus of the AD gate, and you can ground it here. This is the input waveform around 0, whereas the output waveform is shifted by IC into RC drop. Sorry, this will be VCC minus IC into RC drop. So this will be lifted by this voltage, which is nothing but VCC minus IC into RC. So we'll be having the output voltage DC shifted one. You can see it is inverted also. If the input is going high, the output is going low. So and you repeat the, you change the frequency of the signal, note down the input voltage, note down the output voltage, find the gain, and find its gain in dBs. So instead of noting down for different frequencies, so what you can do is you can use that network analyzer. You can plot a Bode plot by varying the frequency from a few hertz to few hundreds of kilohertz. So I'll get the plot immediately for different frequencies. So you try to identify frequency F1 and F2, where the magnitude of the gain is 3 dB down the maximum one. So this will give you the bandwidth F2 minus F1, and you can verify the gain bandwidth, is it constant or not, meaning you change the amplification of this system. Okay, how do you change the amplification? Change the value of Re dash, which will change the gain of the system. So once you change the gain of the system, naturally the bandwidth has to remain constant. So this is how you can do this experiment. Okay, since this is your first electronic amplifier circuit, so I wish you all the best while conducting this experiment. So let me make a brief overview of the things, okay, whatever you are supposed to do it over here. So first and foremost thing is that you have to start with the design verification, the DC condition verification. First, make sure that you are connecting the proper circuit. So you're with, so make sure that you have made this connection. Look for what is Vx, looks for what is VBE, find your IC. If you are through with that, then you apply the AC signal. Make sure that you are having a pure AC signal here with small amplitude. Measure it over here, it's an amplified version, and you change the frequency of the signal, and you verify what is the amplitude. So amplitude will be keep reducing as you increase the frequency. You can do it frequency by frequency by change the frequency, or you can go for a network analyzer where you'll be sweeping the frequency so that you'll get the graph directly. When the frequency is low, the amplitude is, the gain is less. As the frequency comes in the mid band, the maximum gain. So when the further frequency increases, the gain again reduces. So we'll see in the next classes okay, why the frequency for low frequencies gain is less, for higher frequencies why the gain is low, why only at mid frequencies you're going to get the maximum gain. So I hope all of you will get the output without any difficulty. I hope you understood this. So all the best for all the students.